Alright, so now we're ready to use Laplace transforms to solve differential equations with initial values. So let's copy the result from before, but let's replace the letter f by the letter x. So there are two results. The Laplace transform of the derivative is equal to s times capital X minus x of 0, and the Laplace transform of the second derivative has three terms: s squared times x minus s times x of 0 minus x prime of 0. Right, so now let's use that to solve a differential equation. So let's consider the differential equation x double prime minus 3x prime plus 2x equal to 0. And the initial condition is x of 0 is 2, x prime of 0 is negative 1. So now the first step is to apply Laplace transforms on both sides. So we get Laplace transform of x double prime minus 3 Laplace transform of x prime plus 2 times Laplace transform of x equals to Laplace transform of 0. And these two terms, we have the result from before. We can replace it by the right-hand side. So this is equal to s squared times x of s minus s times x of 0 minus x prime of 0 minus 3 times this is equal to s times x of s minus x of 0 plus 2 times the Laplace transform of x is just capital S, x. And the right hand side is 0 because the Laplace transform of 0 is 0. Now we can use the initial values. X of 0 is 2, that's here and here. And x prime of 0 is negative 1, so this is negative 1. Alright, so the left hand side now equals to s squared times x of s minus 2s plus 1 minus 3s times x of s plus 6 plus 2x of s equal to 0. And let's move terms around. So we get s squared minus 3s plus 2 times x of s is equal to 2s minus 7. Okay, so x of s is equal to 2s minus 7 over s squared minus 3s plus 2. And the denominator factors into s minus 1 times s minus 2. And we want to split this into two fractions, so we're going to use the method of partial fraction. So the denominator factors into s minus 1 times x minus 2. So this is, we can assume this is equal to a over s minus 1 plus b over s minus 2. And let's take this equation and multiply by s minus 1 times s minus 2. So we get 2s minus 7 equals to a times s minus 2 plus b times s minus 1. Now the trick is, if we plug in s equal to 2, then the a term cancels and we get negative 3 equals to b right away. And we can do the same trick. So if we plug in s equal to 1, then we get negative 5 equals to negative a, which tells you a is 5. So basically we can, now we have x of s is equal to 5 over s minus 1 plus negative 3 over s minus 2. But this is the Laplace transform, so we can solve for our x of t. This is just the inverse Laplace transform of our function, or of capital X. And this is equal to 5 times the inverse Laplace transform of 1 over s minus 1 minus 3 times the inverse Laplace transform of 1 over s minus 2. And if you look at the table, this is equal to e to the t, and this is equal to e to the 2t. So the solution is x equal to 5 times e to the t minus 3 times e to the 2t. All right, so let's do a different example. So let's consider the example that x double prime plus 4x equals to sine of t. And to make things easier, let's assume the initial condition is x of 0 is 0 and x prime of 0 is also 0. The first step is the same. We take Laplace transforms on both sides, so we get Laplace transform of x double prime plus 4 times Laplace transform of x equals to the Laplace transform of sine t. And then let's recall, this is equal to s squared times capital X minus s times x of 0 minus x prime of 0 and plus 4 times, this is by definition capital X. The right hand side is the Laplace transform of sine t, which if you look at the table from the previous section, it's equal to 1 over s squared plus 1. Okay, so it's a good thing that the initial condition is all 0, so neither of these terms are here, which makes things better. So we get s squared plus 4 times x of s equals to 1 over s squared plus 1. So x of s equals to 1 over s squared plus 1 times s squared plus 4. And here again, we're going to use the method of partial fraction. So the denominator has two factors, s squared plus 1 and s squared plus 4. They're both quadratics, which doesn't further factor. So we have to assume the numerators are linear terms. So this is as plus b, cs plus d. But here's some trick and observation you can make. So this, notice that this is an even function. It only contains s squared terms. So that tells you the right-hand side also has to be even. Both terms have to be even, which tells you that there shouldn't be a s term in the numerator. So which tells us that a and c are both equal to 0. Okay. Now we can multiply by s squared plus 1 and s squared plus 4. So we get 1 is equal to b times s squared plus 4 plus d times s squared plus 1, which this simplifies into b plus d times s squared plus 4b plus d. Compare the coefficients, we get b plus d equal to 0, 4b plus d equal to 1. This is not hard to solve. This tells you that b is negative d, and you plug it in here. So we get negative 4d plus d is 1, negative 3d is 1, so d is negative 1/3, which tells you that b is 1/3. So our solution is our capital X is equal to 1/3 over s squared plus 1 plus negative 1/3 over s squared plus 4. Again, this is the Laplace transform capital X. To find little x, which is what the initial equation asks for, we need to take the inverse Laplace transform. So we take the inverse Laplace transform of these two fractions. Because it's linear, so we can take the constants out. And if you refer to the table, this is equal to sine of t, and this is equal to sine of 2t, but over 2 because we need a 2 here on top. So the solution is equal to 1/3 sine t minus 1/6 sine 2t. All right.